journey into a cutting-edge framework, harmonic substrate gravity, or HSG. It's a perspective that might just change how you visualize the entire cosmos. In traditional physics, we often treat space-time as a smooth, passive manifold, like a stage where actors play their parts. But in HSG, we propose that space-time is an emergent harmonic substrate. Imagine it more like a vibrating fluid or a resonant medium rather than a static background. This substrate has a heartbeat, the vacuum ground state frequency, which we label as $F, $0. This frequency represents the fundamental state of the universe when it's at rest, providing the baseline for all physical interactions. What's truly fascinating is that this harmony isn't random. It's governed by the golden ratio, $phi. We find that this ratio, roughly 1.618, appears in the very geometry of gravitational resonance, acting as a universal constant for stability and balance. So, what are gravity and dark energy in this model? They aren't mysterious external forces. Instead, they are simply deviations, or ripples, in this ground state frequency. When the substrate shifts away from its $F, $0 baseline, we experience those changes as gravitational pull, or the expansion of the universe. On our look at the substrate's frequency, let's examine the physical axioms that define the HSG framework. These are what we call the foundational postulates. Postulate 1 establishes our baseline, the harmonic ground state frequency, $F, $0. As you can see, it is an incredibly high value, approximately $1.146 times 1043 Hertz. This represents the fundamental vibration of space-time itself at its most stable level. Next, postulate 2 gives us the $phi harmonic stability principle. This formula tells us that stable higher-order frequencies must follow a geometric progression based on the golden ratio $phi. Essentially, nature prefers these harmonic intervals to maintain structural integrity. In postulate 4, we define the energy hierarchy. The specific ratio of kinetic to potential energy is defined as $1, phi, $3. This isn't just a random number, it's the exact ratio needed to balance the energy density within the substrate's geometry. Now, it's important to note that while these began as postulates or assumptions in earlier versions, in the current version 4, we've moved toward deriving these values from deeper mathematical mechanics. We're moving from "this is how it is" to "this is why it must be so." Let's see how this math translates into the actual HSG action. Building on the logic we just covered, let's see how these principles translate into a formal mathematical framework. We're moving from the why to the how by defining the HSG action. Look at equation A1 here. This is our complete action S. You'll recognize the first part as the standard Einstein-Hilbert action from general relativity. But we've added a crucial term, the potential function V, which depends on the frequency deviation ΔF. This frequency potential is what allows the harmonic substrate to interact with the curvature of space-time. It represents the energy density stored in those subquantum oscillations we mentioned earlier. A key highlight of this framework is the derivation of the coupling constant, alpha. As you can see, alpha is defined as the square root of 3 divided by the golden ratio, phi. Using the golden ratio isn't just aesthetic. It's mathematically necessary for the stability of the frequency harmonics in an expanding universe. Finally, let's examine this potential curve. This line chart shows how the potential V decays exponentially as the frequency deviation increases. This tracker behavior is what allows the theory to naturally mimic the effects of dark energy without needing a cosmological constant. It's elegant, self-regulating math at work. Building on the self-regulating logic we just explored, let's examine the modified Einstein field equations that govern this framework. On the left, we maintain the classic curvature terms you're already familiar with. The breakthrough is on the right side, the addition of the frequency stress-energy tensor. This term represents the physical interaction between matter and the harmonic substrate itself. Look at the physical interpretation here. When the frequency deviation, delta F, is positive, it accounts for standard mass and the gravitational attraction we observe in typical matter. However, when the deviation is negative, it drives the expansion effect. This provides a unified explanation for dark energy without needing to add it as an arbitrary constant. Finally, notice the classical recovery. In the limit where the new tensor approaches zero, the system returns perfectly to standard general relativity, ensuring all our previous astronomical observations remain valid. In this simulation, we'll explore how local mass and cosmic expansion cause deviations in the substrate frequency, $F, $0. Increasing the local mass creates a positive frequency deviation, delta F is greater than $0, shifting the substrate towards a higher energy state. At high mass concentrations, the substrate frequency intensifies, creating a singularity potential where gravity is strongest. Conversely, cosmic expansion induces a negative frequency deviation, delta F is less than $0, effectively stretching the harmonic substrate. In a cosmic void, the expansion rate dominates, resulting in a significant drop in the local frequency substrate. The phi harmonic balance occurs when mass and expansion reach a ratio that supports stable frequency shells. Experiment with the sliders to see how the stress-energy tensor interacts with the substrate to define space-time geometry. Now that we've explored the conceptual framework of the substrate, let's dive into the core derivation of the dark energy equation of state. This is where the mathematical elegance of harmonic substrate gravity really begins to manifest. We start with the thermodynamics of a scalar field in an FRW cosmology. Note how we define our energy density and pressure traditionally. These depend on a chosen potential, which often feels like guesswork in standard models. However, in HSG, the golden ratio phi dictates the relationship. By applying these specific algebraic identities, like phi plus 1 equaling phi squared, we can constrain the evolution of the field based on the geometry of the substrate itself. When we look for the tracker solution, we arrive at this striking result. The equation of state parameter W equals -1 over phi. This yields a value of approximately -0.618. Crucially, this happens because the ratio of potential energy to kinetic energy is forced by the harmonic geometry to be phi cubed. It's a stable attractor. Up next, we'll verify this numerically to see how it compares with observational data. Building on what we just covered regarding the stable tracker solution, we now need to verify these results numerically. This is where the abstract math meets rigorous computation to ensure our theory holds up under scrutiny. To test the stability, we integrated the system's differential equations using 4 distinct and independent initial conditions, labeled IC1 through IC4. Notice that no matter how we start the simulation, the trajectories all head toward the same destination. The statistical error bound for this convergence, as shown in this formula, is extremely tight, less than 10 to the power of -4. This level of precision confirms that the tracker is not just a mathematical curiosity, but a genuine cosmological attractor within the HSG framework. If you look at this comparison table, you'll see the initial frequency deviations versus the final values of the equation of state. Despite the wide range of starting points, the system effectively forgets its initial state and settles into the stable attractor. This helps solve the fine-tuning problem we often see in other dark energy models. Building on the numerical stability we just covered on the previous page, let's see how harmonic substrate gravity actually compares to the standard general relativity we all know. It's helpful to think of this not as replacing Einstein, but as reinterpreting his geometry through the lens of frequency. In standard GR, we talk about space-time curvature. In the HSG framework, we describe those same effects as frequency gradients. Instead of an object following a curved path or a geodesic, It is simply following a path of frequency synchronization within the substrate. Take black holes, for instance. Standard physics sees them as gravitational singularities where density becomes infinite. HSG offers a more physical interpretation. They are frequency singularities where the oscillation of the substrate reaches a critical limit. And look at lambda, the cosmological constant. In this model, it's no longer just a mathematical constant added to the equations. It represents the fundamental ground state energy density of the universal harmonic substrate itself. Finally, frame dragging is modeled as rotational frequency vortices. Our TA often uses a great analogy for this. AI Zhujiao. That's right. Think of a massive object spinning in a thick fluid. It creates a swirl or a vortex. In HSG, that swirl is the shift in frequency as the substrate interacts with the rotation. So we're basically floating in a giant cosmic smoothie. I knew the universe was just one big blender. Building on that cosmic smoothie analogy, it's time to see if our HSG framework actually matches the flavor of the real universe. As we discussed on the previous pages, a theory is only as strong as its falsifiable predictions. Today, we're looking at the hard astrophysical evidence. Our first major prediction concerns the dark energy equation of state, represented here as W. While the standard LCDM model insists that W is exactly -1, the HSG framework predicts a value of -1 over phi. This isn't just a minor tweak, it's a fundamental difference in how we view cosmic expansion. Now, look at this data comparison. Recent DESI-DR2 observations have shown deviations from the standard model ranging from 2.1 to 3.5 sigma. In the world of physics, that's a significant tension. HSG naturally resolves this by placing the attractor exactly where the data seems to be drifting. Moving from the macro to the micro, we also predict phi harmonic overtones in gravitational wave ringdowns. If the substrate is real, the echoes of merging black holes should follow this frequency scaling. F, n equals phi to the power of n times the fundamental frequency. Finally, we even see this pattern in celestial mechanics, where orbital period ratios cluster near phi. It's as if the universe has a preferred harmonic signature. Before we move to our final assessment, let's think about the implications of these findings. As we move toward the conclusion of our session, let's look at how the theoretical work we've discussed is being translated into formal scientific research. We are currently in a very active phase of validation and publication. A major milestone has been the rigorous derivation of the Christoffel symbols for the dollar, phi dollar, harmonic perturbations. This math is essential. It's the bridge that lets us calculate exactly how the harmonic substrate influences the motion of particles and light. Crucially, this derivation has allowed us to confirm the second-order post-Newtonian recovery of general relativity. This is a big win because it proves that HSG doesn't break the classic tests of gravity that Einstein already passed. On the observational side, our primary challenge right now is noise reduction. We are working on separating the specific dollar, phi dollar, clustering signals from standard mean motion resonances. Think of it as tuning a radio to find a precise frequency amidst a lot of static. Finally, the culmination of this work is heading to peer review. We have papers in preparation for MNRAS Letters and Foundations of Physics. It's an exciting time to be involved in this framework as we move from theory to formal consensus. We've journeyed from DESI. To wrap up our session, I've prepared a final assessment to consolidate everything we've discussed. This is your chance to see how these complex mathematical pieces fit together into a single, elegant framework. As you tackle the first two questions, focus on the derivation we saw earlier. Remember